1.3 OSPF Operation. And let's begin with 1.3.2. That's the OSPF operational states. When an OSPF router is first connected to a network, it goes through four major steps before it's ready to forward traffic. These steps are create adjacencies with neighbors, exchange routing information, calculate the best routes, and reach convergence. When two OSPF routers become neighbors, they do not immediately exchange routing information. Instead, they progress through a series of neighbor states to ensure communication is working correctly before synchronizing their database. The first four states are done, initial, two-way, and exchange states. Let's begin with the done state. The done state is the starting point. At this point, no hello packets have been received from any neighboring router. The router assumes there are no neighbors. It begins sending hello packets periodically out all OSPF-enabled interfaces. If another router responds with a hello packet, the state changes to initial. Think of it like introducing yourself to someone for the first time. And then the second one is the initial state. The initial state means the router has received a hello packet from a neighbor. However, communication is still one way. The received hello packet contains the neighbor's routing ID, the OSPF parameters. At this point, the receiving router has heard the neighbor, but the neighbor has not yet confirmed hearing back. When the router sees its own router ID listed inside of the neighbor's hello packet, communication becomes bidirectional. The state changes to two-way. The third one is the two-way state. The two-way states confirm that communication works in both directions. Both routers can send hello packets, can receive hello packets, recognize each other as neighbors. This is called bidirectional communication. On Ethernet, if the network is Ethernet or another multi-access network, the routers performed a designated router, DR, and the backup designated router, the BDR election. The DR and the BDR reduce unnecessary routing updates on shared networks. On point-to-point links, there is no DR or BDR election because only two routers exist on the link. After the neighbor discovery is complete, the router moves to the exchange start state. The exchange start state prepares the routers for database synchronization. During this state, the two routers determine which router will act as a master and which router will act as a slave. The initial database description DBD sequence number. The master controls the exchange of DBD packets, while the slave follows the master sequence numbers. No routing database exchange yet. This stage simply prepares both routers for the next phase. After the routers complete the exchange start state, they begin exchanging and synchronizing their routing databases. The final OSPF neighbor states are exchange, loading, and full. During the exchange state, the routers begin exchanging Type 2 database description, the DBD packets. Remember that a DBD packet is not the entire routing database. Instead, it contains an abbreviated summary of the router's link state database, the LSDB. Each router compares the received DBD packet with its own LSDB. There are two possible outcomes. If both databases already match, no additional information is needed, and the routers move directly to the full state. If information is missing, the routers proceed to the loading state to request the missing LSAs. Think of the DBD packet as comparing the table of contents of two books before exchanging the missing chapters. And then we have the loading state. During the loading state, the router exchanges the missing routing information. 3 OSPF packet types are used. Type 3 LSR, that's the link state request. This requests missing LSAs. We have the type 4 LSU, that's the link state update, sends the requested LSAs. And then there is a type 5 LS acknowledgement, the LSACK. It confirms the LSU was received successfully. After all missing LSAs have been received, each router updates its link state database. The router then runs the shortest path first, the SPF algorithm, also known as the Dijkstra algorithm, to calculate the best routes. Once the database is complete and the routes have been calculated, the routers move to the full state. The full state is the final OSPF neighbor state. At this point, the link state database, the LSDBs, are fully synchronized. Both routers have identical topology information for the OSPF area. The SPF algorithm has calculated the best routes. The routing tables are fully updated. The routers continue exchanging hello packets periodically to maintain the neighbor relationship. If a network exchange occurs, such as a link failure or a network being added, the routers exchange new LSAs, update the LSDB, rerun the SPF algorithm, and remain in the full state after synchronization. 1.3.3 Establish neighbor adjacencies. Before OSPF routers can exchange routing information, they must first discover their neighbors. This discovery process begins with the hello packet. This figure shows the very beginning of the OSPF neighbor discovery process. At this point, both routers are in the down state. R1 has OSPF enabled and begins sending hello packets. The orange arrow represents the hello packet traveling towards R2. Both routers are currently shown in the down state because no hello packet has yet been received from the other router. This is the first step in the OSPF neighbor discovery. This figure shows the next step in the OSPF neighbor discovery process. Previously, R1 was sending hello packets while in the down state. Now R2 has received R1's hello packets. This figure shows the two-way state in the OSPF neighbor relationship. At this stage, both routers have successfully exchanged hello packets and recognize each other as neighbors. R2 becomes the designated router, the DR, because it has the highest router ID. R1 becomes the backup designated router, the BDR, because it has the second highest router ID. Both routers have the default OSPF priority of 1. The election occurs only because the routers are connected through an Ethernet multi-access network. 1.3.4 Synchronizing OSPF databases. After reaching the two-way state, OSPF routers begin database synchronization. The hello packet has completed its job of discovering neighbors and establishing adjacencies. Now the remaining 4 OSPF packet types are used to synchronize the link state databases. Database synchronization occurs in 3 main steps. Step 1, decide the first router, the exchange start state. Step 2, exchange DBD packets. That's the exchange state. Step 3, request missing information, the loading state. The router first enters the exchange start state. During this stage, they decide which router will start the synchronization process, the master, which router will respond, the slave, the initial database description sequence number. This ensures both routers exchange information in an organized manner. Next, the router moves to the exchange state. They exchange database description packets. The DBD packets contain a summary of the link state database, not the complete database. Each router compares the received summary with its own LSDB to identify any missing or outdated information. If a router discovers that information is missing, it sends a link state request packet requesting the specific records. The neighboring router replies with a link state update packets containing the requested link state advertisements. Finally, the receiving router sends a link state acknowledgement to confirm that the LSU was received successfully. Once both routers have identical LSDBs, they enter the full state. 1.3.5 The need for a DR. On a multi-access network, such as an Ethernet LAN, OSPF routers do not form neighbor relationships with every other router. Instead, OSPF elect a designated router and the backup designated router to improve efficiency. There are two main reasons for this election. One is to reduce the number of adjacencies. The other one is to reduce the LSA flooding. This figure shows 5 OSPF routers connected to the same Ethernet network. Notice the purple arrows. Each arrow represents an OSPF adjacency between two routers. Without a designated router, every router forms a full adjacency with every other router. That means R1 exchange routing information with R2, R3, R4, and R5. R2 also exchange with R3, R4, and R5. R3 exchanges with R4 and R5, and R4 exchanges with R5. Every router communicates with every other router. 1.3.6 LSA flooding with a DR. As the number of routers on a multi-access network increases, the number of OSPF adjacencies also increases dramatically. More adjacencies means more link state advertisements must be exchanged between routers. Every time there is a network exchange, such as a link failure, router reboot, a new network being added, the routers flood updated LSA to all adjacent neighbors. Without a designated router, each router sends these updates to every other router on the network. As the network grows, this creates a large amount of unnecessary routing traffic. The excessive flooding of LSA can increase the bandwidth usage, increase CPU utilization, consume more memory, slow network convergence. This figure shows 5 OSPF routers connected to the same Ethernet network without the designated router. Notice the large number of the purple arrows. These arrows represent the exchange of the link state advertisements between the routers. Because every router has a full adjacency with every other router, each LSA must be sent to every neighboring router. For example, if the router at the top left detects a link failure, it floods a new LSA to all its neighbors. Each neighbor then forwards that LSA to its own neighbors. As a result, the same LSA travels across the network multiple times. This creates a large amount of routing traffic. as the number of routers increases, the amount of LSA flooding grows dramatically. For example, 5 routers generate 10 adjacencies. 20 routers generate 190 adjacencies. Every topology change causes routing updates to be exchanged across all these adjacencies. This animation demonstrates why OSPF elects a designated router and a backup designated router. Initially, 5 routers share the same Ethernet network. The router highlighted in orange is the designated router, and the router highlighted in yellow is the backup designated router. Now assume R2 detects a network change, such as a failed link. So step 1, R2 generates an LSA. R2 creates a new link state advertisement describing the topology change. And then the next step, R2 flushes the LSA. R2 flushes its LSA onto the Ethernet network. Every router connected to that LAN receives the update. All routers now have a copy of R2's LSA. At this point, each router knows about the R2 topology change. After processing R2's update, other routers may also advertise their own link state information. For example, R3 generates an LSA. R3 flushes its LSA across the network. Then R5 may advertise its own LSA. Soon, multiple LSAs from different routers are traveling across the same Ethernet segment. Now the network contains LSA from several routers simultaneously. Each router must receive the LSA, process them, forwarding them, acknowledge them. The amount of routing traffic grows quickly. Remember that every LSA must also be acknowledged with an LSACK. So in addition to the LSAs themselves, router exchange acknowledgement packets. The actual routing traffic is therefore much greater than what is shown in the animation. This animation demonstrates how the designated router reduces OSPF LSA flooding on a multi-access Ethernet network. The router highlighted in yellow is the designated router. Suppose the router on the left detects a topology change. It generates a new link state advertisement containing the updated network information. Instead of sending the LSA to every router, it sends it only to the designated router. And then the designated router receives the new LSA from the sending router. The DR now becomes the central collection point for this routing update. After receiving the LSA, the DR floods a copy of the LSA to every other router on the multi-access network. The original sending router does not need to resubmit the update. Every other router receives the LSA from the DR. Each router updates its link state database with the new topology information. Now every router has an identical view of the network. Notice that only one router, the DR, distributes the LSA to the network. The other routers do not flood the same LSA to each other. This eliminates duplicate LSA transmissions and greatly reduces routing traffic. What happens if another router has an update? If another non-DR router generates a new LSA, the process is exactly the same. The router sends its LSA to DR. The DR flushes the LSA to all other routers. Every router updates its LSDB. The DR serves as a central distribution point for all LSAs on the Ethernet segment. And why use a DR? Without a DR, every router forms an adjacency with every other router. Every router flags LSAs to every neighbor. Every LSA requires acknowledgements. Routing traffic grows rapidly as more routers are added. With a DR, other non-DR routers send LSAs only to the DR. The DR flags LSAs once to the entire network. Fewer adjacencies are required. Less bandwidth is consumed. CPU utilization is reduced. OSPF scales much better on Ethernet networks. Important note, the DR is used only for OSPF control traffic, especially the distribution of LSAs. It is not used to forward normal user data packets. Data traffic still follows the best path determined by the OSPF routing table, not necessarily through the DR.